Hi, this is Chris from Laptastic, and today we're going to investigate the elasticity of human hair. This is the Wikipedia entry for Young's modulus E. You see, E is defined as the stress over the strain. Stress sigma, strain epsilon. Now the stress is defined as the force acting on our hair divided by its cross-sectional area, which will be small and hence difficult to get. The strain is defined as the change of the length of the hair divided by its original length. Now let's use this formula to do our experiment. How can we get the diameter of such a thin thing as a hair? We certainly cannot do a direct measurement. Instead, we're going to do a diffraction experiment. We're going to hit the hair with laser light and look at the pattern that forms behind it. Okay, we're ready to calculate the diameter of the hair. If you want to do this by yourself, skip the next chapter. Now we know the diameter of our hair and can calculate its cross-section. What's the next step? Now we need to apply more and more force to our hair and watch it getting longer and longer. Let's get to it. We've got everything we need to do the data analysis. If you want to do this step on your own, skip the next chapter. Now let's do the data analysis for this experiment. I've prepared a spreadsheet. Here you can see the initial length of the hair, which is 42 centimeters. In this column, I've put the added mass in steps of 5 grams. From this mass, we can calculate the force acting on our hair in Newton. Last but not least, in this column, we have the extension in centimeters. So this, for example, here is 1.3 millimeters. Now we can make a scatter plot. This is the scatter plot. We have the extension on the x-axis and the force acting on our hair on the y-axis. You clearly see, if you look at the data points, that this is not a linear behavior. The linear fit is way off. But if you look at the first 4 data points, they seem to be in a straight line. And indeed, if you look at the data, you can see that from here to here it's 1.3 millimeters, from here to here it's also more or less 1.3, here as well, and then it starts to deviate. So we could try and erase those three values in order to get a good fit. Here is the equation of this fit. You can see the slope of the straight line here. It's more or less 0.4 newtons per centimeter. Now let's look again at the definition of Young's modulus. In order to calculate it, we need the force, the initial length, the cross-sectional area and the extension. Now from our spreadsheet we got this value, which is 0.4 newtons per centimeter or 40 newtons per meter. We also know the initial length of the hair, which was 42 centimeters, and since we know the diameter, which was 35 microns, we can calculate the cross-sectional area. So Young's modulus of the hair I used is between 7 and 8 gigapascal. That sounds like a lot, but isn't. If you look at aluminum, you find a 10 times bigger value. If you look at single-walled carbon nanotubes, you find a value which is even 150 times larger. Let's hope that this new material soon gets available on an industrial scale. It would open up an entire universe of new applications, a space elevator for example. That's it for today. Hope you liked it. Don't forget to hit the subscribe button.